All right, well, this is not our last section in Chapter 1. It is the last section about equations. So 1.4 was linear equations, 1.5 is quadratic equations, and 1.6 is titled Miscellaneous Equations, which is a very vague title, I think. But what it does is it encompasses a lot of types of equations, and some of the ways that we solve them are similar, some aren't, but they all get sort of mushed together in this section. One type of equation that we're going to take a look at in this section are roots. Now, many of the types of problems, this one in particular, once I get my answer at the end, you need to make sure it really works. Because I have a radical. And things happen really funny when things get squared, right? Negatives change to positives sometimes. So it's possible at the end of a problem that starts out with a radical that I get an answer that really doesn't work. So anytime I've got a radical involved, I need to make sure that I'm checking my solution at the end. So I have a square root, and there's something sort of embedded underneath it, that x. And if I'm going to be solving for x somehow at the end anyway, I can't have it underneath a square root. Does that make sense? It's got to come out. And the way that we eliminate square roots is that we square. That's the inverse operation. So we are going to square both sides. Now, squaring a square root, inverse operations, just cancels them and leaves me with x minus 1 on the left. So again, going back to some of the errors I saw on the test, you cannot just square the x and square the 7 on the right. You have to square the quantity x minus 7. So that means I have to do x minus 7 times x minus 7. That's what squaring a polynomial, in this case a binomial, means. So my x minus 1 on the left is good. On the right, I have x squared. On the inside, I have negative 7, and on the outside, I have negative 7x. So that's negative 14x. And then my last terms, let's go with that one, are going to be the 2 7s multiplied to give me a positive 49. Okay, so far so good? Excellent. Now, it's quadratic. We just did a whole chapter, a whole section of our chapter, right? 1.5, solving quadratic equations. So we're just back in the same section that we just left, 1.5. Quadratic equations have lots of methods. We can complete squares. We can use quadratic formulas. We can factor. Lots of choices. When it works, factoring's the easiest. So my go-to is usually factoring. And to be honest, my second, when factoring doesn't work, is quadratic formula. I would be hard-pressed to ever look at this and say, let's complete the square. It's just not where I'm led to myself. If you want to complete the square, more power to you. That's great. But we're going to actually do this one with factoring. So I need everything together on the same side. And since my x squared is positive and it's already on the right-hand side, I'm going to move everything over to the right-hand side on this one. All right? So I'm going to move my x. And I'm going to move it where it goes. It's going to combine with that negative 14. And I'm going to add my 1 like that. So that leaves me with a 0 on the left. On the right, I have x squared. Negative 14 and negative 1 is negative 15x. And then 49 and 1 is 50. Okay. I'm going to attempt to factor with trial and error because I have that linear x squared, or not linear, but that coefficient in front of x squared is a number 1. So it does, in fact, give me the x and the x quite nicely. The sign here being positive at the end means the signs match. The sign in the middle being negative means that they are negatives. So I have a negative and a negative. Because the negative times a negative is a positive 50. Negative plus a negative is negative. Last piece, I need two numbers that multiply to 50 and add to 15. What are they? 10 and 5. Okay, now what we did in the previous section after we factored is we set each of the factors equal to 0 to solve. So x minus 10 equals 0, x minus 5 equals 0. We're going to add 10 to both sides. So x is 10. Add 5 to both sides, and x is 5. Now, I mentioned this at the beginning, and I mentioned it again. We need to go back up to the original question and see if it'll work. Okay, so I talked a lot about this in the quadratic section. Here, it's absolutely crucial. And the reason is because one of these is not going to work. And if you give me both of these answers, then one of them is simply wrong. Not because you did any work wrong, but because you just failed to do the last step of checking. So let's start with 10. So I'm going to actually write them out so that you can see them. I'm going to put in here, I've got the square root of 10 minus 1 on the left, and then I have 10 minus 7 on the right. So the 10 minus the 1 is 9, square root of 9. What's the square root of 9? 3. On the right, what's 10 minus 7? 3. So these two are equal. This one works. X equals 10 is really a solution to our problem. It actually is. So this is one of my solutions. The other one, 5. I have the square root of 5 minus 1 equals, and on the right-hand side I have 5 minus 7. Do you see the problem that's going to come into play? On the right-hand side here I end up getting a negative. So how did that happen? Well, it happened because I squared it, right? I squared a negative at the original part of the problem. I didn't know it was negative when I did it, but that's what ended up happening if I tried to use that value. So the sign became positive as I was solving the problem. So on the left I have the square root of 4. On the right I have negative 2. And the square root of 4, given and written as square root of 4, is not positive or negative. It's positive. It's called a principal square root. The only time things come up to having pluses or minuses is when you introduce the square root into the problem. And we didn't do that on this. It was already there. So these two do not equal, which means this is not really a solution. So what does it actually mean? It actually has a name. It's called extraneous. I feel like it's kind of like the word erroneous, right? It's sort of irrelevant. It doesn't actually really matter. It doesn't work in this problem. Okay, any questions on that one? Okay, how is the next problem different than the one we just did? It's got a radical in it, but how's it different? There's two radicals. That actually makes things quite different. I can't just square both sides and the radicals go away. Okay? So, as I'm working with this, please remember you cannot just square individual pieces of things. That's not true. And I know I've shown you this before, but let me show you again. It is not true, for example, that 3 squared plus 4, or I should say it this way, 4 squared equals 7 squared, right? 3 plus 4 is 7. That's true. But 3 squared plus 4 squared is not 7 squared. So you can't just square each individual little piece. It's absolutely not a true statement. So what do you have to do? Well, you actually have to do it a lot like we did this problem over here, where you square complete and total sides of equations. But it's really bad because I have square roots on the left-hand side that are going to come into play with one another. So the first thing that I'm actually going to do is to separate the square roots. Okay? So the first thing we're going to do is we're going to add the square root of x to the right-hand side. Now, it doesn't change the fact that I still can't square all the individual little pieces, but it will keep me from having to multiply the square root of x and the square root of x plus 40 together, which is desirable to not have to do that. So on the right-hand side, I have 4 plus the square root of x. It looks a little bit more like the last problem now, because at least I have just a square root isolated by itself on the left. That part's similar. And the process that I go through next is also quite similar. I am going to square things. And the square and the square root on the left do cancel, because I have a square root of something all by itself raised to a power that's squared, so this will give me x plus 40. The problem is, just like on this last problem, that I can't say x squared and 7 squared, I cannot say 4 squared and square root of x squared. And even as I say it, I'm bracing myself for the fact that on the next test, if there's a question like this, at least half of you are going to do just that. And I'm going to cringe, and I'm going to write the word no, and there's going to be an exclamation point. So write yourself a note in your notes right now. Don't do that. You can't square the individual pieces. So what can you do? Well, unfortunately, all you can do is multiply it by itself. So the square root does not officially go away, at least not yet. I have x plus 40 on the left. On the right, the first terms, 4 times 4 is 16. My outer terms give me a 4x. I should have said 4 square root of x is what I meant to say. My inner terms also give me a 4 square root of x. And then the last terms multiplied together do cancel my radical. Square root of x times square root of x is x. So the last piece eliminated the radical. I do still have a radical involved, but the last piece eliminated that portion of it. All right, so now what? Well, I need to isolate my radicals again. Just like I did at the beginning, I tried to get a radical by itself. Well, I need to combine pieces and try to get the radical that still remains by itself. So we can actually subtract the x. That's actually really nice. Did you notice that? That x that's not inside the radical is actually eliminate when it subtracts. I'm actually going to move this 16 as well because I can combine it with the 40. Those are like terms. So the negative x and the x add to 0. 40 and negative 16 is 24. These are adding to 0 and these add to 0. These two can combine as well. 4 square root of x plus 4 square root of x is 8 square root of x. So if I'm trying to get my square root alone, what would I do next? Yeah, I would divide by 8. That gives me a 3 equals the square root of x. And then what would be my last step? Square it. My goal is to find out what is x. So I will square it to eliminate the radical, and I will find that x is 9. There were radicals, though, involved at the beginning. I only end up with one answer on this one, right? The last problem I ended up with 2 answers to check. I still need to check the answer. It's possible in doing all of that that I have no solution, that this 9's not going to work. It's also possible it does work, and I need to confirm to see. So we will put in here a square root of 9 plus 40 minus the square root of 9, and the question is, will it equal to 4? 9 plus 40 is 49. All right, so what's the square root of 49? And what's the square root of 9? And does, in fact, 7 minus 3 equal 4? It does. So I do have a solution, and it does work this time. One solution. There's one more problem that involves roots. It doesn't look like it initially, but it does. Before I switch my screen, any questions on this particular one? I think this is the hardest question with roots, is ones where there's 2 roots involved. So, all right, let's take a look at the next one. It doesn't look like there's roots, but it's this part C of the same question, so there must be some roots in there, right? All right, there are. I think we've talked about, though I can't remember at this point since we've had some videos and been gone some, about the fact that rational exponents, m over n, have a radical form. Have we talked about that before? Some of you have had me in another class, so I don't want to look at you because I don't know if you've done it with me before or actually here. When I have a rational exponent, rational means fractional, in the case I'm looking at right now, fractional exponent, the n that's the denominator becomes the index of the radical, and the m is the exponent of the problem. So that's how it's rewritten in radical form, which is why this problem really does have roots in it. This 3 makes it a cube root, and then the x will have a power of the 2. Okay, now on the last problem, the very last step we did, we had the square root of x equals something, and we talked about the fact that the way we eliminate that square root is that we square, right? Much like on this one, the way we eliminated the square root is that we square. Over here, I have a cube root. So how do you think I would eliminate a cube root? You cube it, exactly. So we're going to cube both sides. We're sort of working from the outside in. Cube root, we're eliminating it first. So I'm going to be left with an x squared on the left because the cube root and the cube cancel. Now, 1/2 cubed means that I have 1 cubed on top, which is 1, and 2 cubed on bottom, which is 8. So the problem is already better than where I was, right? I do not have radicals any longer involved. In fact, this actually becomes a problem like from section 1.5 that we just did. X squared on the left, number on the right. So we will take a square root. We will make it x on the left because the square root and the square will cancel. Whoops. I took a square root. You took a square root, which means we introduce a positive or negative, because we inserted that into the problem. It was not there, right? Cube root was there, but the square root was not. So now I need the square root of 1. That's kind of nice. And I need the square root of 8. All right, well, the square root of 1 is 1. So that's great. Square root of 8. Well, 8 is 2 times 2 times 2. So 2 of those 2's match, allowing them to come out as a 2 out, and there's a square root 2 underneath. The reality is there's nothing wrong with this answer per se, except the fact that whoever along the way decided that radicals in the denominator are just, I don't know, they taste bad or something. I'm not really sure what it was. But we have this convention in mathematics that says we don't leave a radical, like a radical 2 here, underneath the denominator. We don't do that. So what do? Well, we've talked about this before. We will simply multiply, in this case, by that radical. There's no conjugate because there's no addition or subtraction. It's just the denominator, square root of 2, that we had there. So my x equals, I have the plus or the minus. I have a square root of 2 on top. I have this square root of 2 and this square root of 2 giving me a 2. I have this 2 in front giving me another 2, so there's 2 times 2 or a 4 in that denominator. Now, do not be tempted to simplify the 2 on top with the 4 on bottom.
I think it's going to take a closure test.
Okay. Because one's underneath the radical and one's not. So we can't simplify that any further. It just has to be left written that way. Any questions on that one? That's our last radical one that we're going to do. I don't mean radical like extreme. Like radical with roots, right? Yeah. All right. Another type of problem we're going to look at is absolute values. So absolute value equations, we have seen them before, but we've seen them only with linear equations. Now we're going to do them with quadratics and other pieces as well. You'll notice it's quadratic because I have x, or in this case a, squared in the problem. Okay? Now, this is another place where people really struggled on your test with linear equations that had absolute values. So they were linear absolute value equations. If there's an absolute value involved, it means that what's inside of the absolute value could equal what's on the other side or equal the opposite of what's on the other side. So it could equal a squared minus 1 could equal 1, or that a squared minus 1 could equal the opposite of what's on the other side, namely negative 1. What are we saying? Well, we're saying that if this thing equaled 1, the absolute value of 1 would be 1. If this thing equaled negative 1, the absolute value of negative 1 would be 1. That's where that's coming from. So what ends up happening is I just have 2 quadratics to solve. It's just the first step that's different than what we've seen before. So at this point, what you'll notice on this particular problem is that I have a squared and I don't have any a's, right? So that means that square root principle is really helpful here. I can add my 1 to both sides. I have a squared on the left, and I have a 2 on the right. What would I do then? Square root. And since we put the square root on, we put a plus or minus. The square root and the square eliminate on the left, leaving me with a. And I just have square root of 2 on the right. I have 2 of them. That's 2 answers. The other part of the problem, the other equation, when I add my 1, it's actually very friendly on this particular one. These, of course, add to 0 on the left. I have a squared on the left. And what do I have on the right? 0. And I take a square root, and what do I get? What's the square root of 0? 0. Because 0 times 0 is 0. So, interestingly enough, I actually end up with 3 solutions on this particular problem. 0, positive square root of 2, and negative square root of 2. You're welcome again to check these to make sure you didn't make a mistake throughout, but it doesn't come into play like these did, right? I should have checked this with you. I'll go back and do that in here in just a second. But it doesn't come into play like the ones with the radicals involved. And the reason is because I don't have that happen when I have absolute values. So you aren't checking so much for the purposes of making sure you don't have extraneous solutions. You could be checking to make sure you didn't make a mistake. On this one, oops, I skipped it. On this one, there's actually not quite the same need to check it as there was before. And the reason that there is not is because I don't have a square root, I have a cube root. And cube roots preserve signs. The cube root of something negative is still negative. Cubing something negative stays negative. It really only comes into play where we lose signs when we're squaring, raising to powers of 4. It's those even powers that cause problems. This one doesn't have that. It has something odd. It's a cube root. So that's why it wasn't necessary, and I should have mentioned that. This one's a little interesting because it has 2 radicals, or 2 absolute values. And in theory, there's actually 4 things that could happen. The pieces that are inside could both be positive, right? They could, in which case we'd just lift the absolute value signs off and they'd be equal to each other. That's one possibility. And in fact, it's such a good possibility that we're going to write it down. One possibility is that we simply have 2x minus 3 actually really equals 2x plus 7 because they're both positive. So this is option 1. Option 2 is that they could both be negative. Okay, well, what would we do if they were both negative? Well, we'd change their signs. So we'd multiply them both by a negative. So negative times 2x minus 3 equals negative times 2x plus 7. But couldn't I just now divide both sides by a negative and it become the same problem I already did? Wrote down anyway. This isn't any different. If the signs of both of them are positive and I remove the radical or the absolute values, or the signs are both negative and I put a negative in front of both of them, I don't have anything different. This, when I multiply or divide by a -1 now, because that's what I would do or could do to solve this, becomes 2x minus 3 equals 2x plus 7, and it's the same as number 1. So that's not going to give me any new information. It will not give me any new values. If I forget that and I actually solve it, I'll get the same answers I did before. Okay, so one option they're both positive, one option they're both negative. What's the third option? One's positive and one's negative. And it's actually 2 options, right? I could have the one on the left positive, the one on the right negative, or I could have the one on the left negative and the one on the right positive. But again, much like this here, it doesn't really matter. The fact that the signs are different doesn't matter which one's positive and which one's negative. Their signs are just different. So my third option is that the signs don't match, in which case we'll just leave the left-hand side one the same and make the right side one negative. Doesn't matter which one we do. They'll work out to being the same answer. So this one's not really necessary. There's really only 2 options. The signs match, in which case the absolute values just disappear. The signs are different, in which case one of them, absolute value disappears. The other one, the absolute value has a negative that's going to have now in front of the values. So let's solve this very quickly. On number 1, where it's listed as 1, you'll notice that we have a problem, quote unquote. As I do this, what happens when I subtract the negative 2x from both sides? Yeah, there's no more x's, right? So I have negative 3 on the right, and I have positive 7 on the left. I said it wrong. Negative 3 on the left, positive 7 on the right. And that's not true. So this option has no solution. That doesn't always happen. That just happened on this one. There's no solution if the signs actually were the same. So that's not possible. The other option down here, this is the signs that were different. So I have negative 2x now minus 7, because I'm distributing that negative through. Okay, let's finish this up. 2 shakes of a lamb's tail. We'll add the 2x to the left. We'll add the 3 to move it to the right. And as we do that, we have 4x on the left. I have negative 4 on the right. And if I divide by 4, my answer is negative 1. And I only end up with 1 solution. I could have 2 solutions for these problems. That is possible. But on this one, I ended up with only 1. All right, we have one more type of problem in this section that we're not finished with, which means, and I was kind of hoping that might actually be the case, which means that we will finish that last piece up. It's probably 10 minutes or something like that on Thursday. I'll push the 1.6 to be due until next week, and the quiz that's supposed to be Thursday will be pushed to next week. So you will have quite a bit over the weekend because you will finish 1.6. We will definitely do 1.7. And we may or may not be working all the way into 2.1 and finishing that. I need to look at the schedule, okay? But the quiz will be pushed. The homework 1.6 will be pushed, all right? Have a great evening, guys. Make sure that you're working on tests, redo, corrections, reworking, whatever you want to call it. It's in the announcements in Canvas.